There's a place at the edge of our universe where the rules of reality seem to break down, a vast, empty darkness so immense it defies comprehension. Picture this, a region spanning billions of light years, utterly devoid of stars, galaxies, or even the faintest glimmer of light. This is the mysterious void at the edge of the universe, and it might be growing larger as we speak. What could possibly create such a cosmic anomaly? And what does its existence and potential expansion mean for our understanding of space, time, and everything in between? For centuries, humans have gazed at the night sky, mapping constellations and marveling at the brilliance of distant stars. But this void is different. It's not just an absence of light, it's a gaping hole in the fabric of the cosmos itself, challenging everything we thought we knew about how the universe is structured. Some scientists believe it could be a relic from the earliest moments of creation, a scar left behind by forces we're only beginning to comprehend. Others speculate it might be evidence of something even more extraordinary, a doorway to realms beyond our own, or a flaw in the very nature of reality. This isn't just a story about distant space, it's a puzzle that touches the very core of existence. As we dive into the mysteries of this expanding void, we'll explore the cutting-edge theories that attempt to explain it, from cosmic inflation to multiverse hypotheses. You'll discover how astronomers stumbled upon this enigma, the tools they're using to study it, and why its existence could rewrite the textbooks of physics. So buckle up, we're about to journey to the edge of the known universe, where the answers we find might be as unsettling as they are awe-inspiring. By the time we're done, you'll never look at the night sky the same way again. The year 2007 marked a turning point in our cosmic map, making a moment when astronomers peered deeper into space than ever before and found nothing. That's right, nothing. While scanning the skies for distant galaxies, researchers uncovered a staggering absence, a hole in the universe stretching 1.8 billion light-years across. They called it the Eridanus Supervoid, and its existence sent shockwaves through the scientific community. Imagine looking at a bustling city from above, only to spot a vast, silent district where no buildings, no streets, no life exists, just an inexplicable blank space. That's what this cosmic void represents on an unimaginable scale. The discovery wasn't just surprising, it was borderline unsettling. According to our best models of the universe, matter should be distributed somewhat evenly, like sprinkles mixed into cake batter. But the Eridanus Supervoid wasn't just a sparse region, it was a near-total vacuum, a place where galaxies should have been but weren't. To put its size into perspective, if you could travel at the speed of light, it would take you nearly 2 billion years to cross it. That's longer than multicellular life has existed on Earth. So how did scientists find it? The breakthrough came from a clever combination of sky surveys and cosmic microwave background data, the faint afterglow of the Big Bang. When researchers noticed an unusual cold spot in this ancient light, they realized it aligned perfectly with the void. The explanation: light passing through such an enormous empty space loses energy, like a traveler growing weary crossing a desert with no oasis in sight. This phenomenon, known as the integrated sachs-wolfe effect, provided the first hard evidence that the void wasn't just an observational fluke, it was a real, physical structure with tangible effects on the fabric of the cosmos. But the real mystery lies in how it formed. Some theorists suggest it could be a remnant of the universe's infancy, a bubble left behind by quantum fluctuations during cosmic inflation. Others propose even wilder ideas, like the possibility that it's the imprint of a collision with another universe in the multiverse. What's certain is this: the Eridanus Supervoid forces us to rethink our assumptions about how the universe grows and evolves. If voids like this can exist, what other surprises are lurking in the darkness? The existence of this colossal void isn't just a cosmic oddity, it's a riddle that forces us to question the very foundations of physics. One leading theory suggests it's a fossil from the universe's explosive birth, a bubble frozen in time. Picture the cosmos in its first trillionth of a second, a seething ocean of energy where quantum fluctuations tiny, random ripples in space-time could have stretched to unimaginable scales during inflation. If one of these fluctuations left behind an underdense region, it might have grown into the vast emptiness we see today, like a single breath expanding into an endless cavern. But not all scientists are convinced. Some propose an even more mind-bending explanation. This void could be a bruise from a collision with another universe. In the multiverse theory, our cosmos might be one bubble among countless others in an infinite cosmic foam. If a neighboring universe brushed against ours in the distant past, the energy of that impact could have shoved matter aside, leaving behind this staggering emptiness. It's as if we're finding fingerprints on the walls of reality, hinting at forces beyond our perception. Then there's the radical idea that the void isn't a structure at all, but a glitch. Some theorists speculate that what we're seeing could be a rare statistical fluke, a cosmic illusion created by the way galaxies cluster. Others wonder if it reveals a flaw in Einstein's theory of gravity itself, suggesting that on the largest scales, the rules of relativity might need rewriting. Imagine discovering that the map of the universe you've been using has been subtly distorted all along, and this void is the first clue. What makes these theories so compelling is how they intertwine. The quantum fluctuation idea ties into our understanding of the Big Bang, while the multiverse hypothesis challenges us to think bigger than a single cosmos. Even the glitch theory forces us to confront how little we truly know about gravity's behavior over billions of light years. Whatever the answer, studying this void isn't just about solving a puzzle, it's about testing the limits of human knowledge. Every observation, every calculation brings us closer to either confirming our boldest theories or discovering something entirely unexpected. And that's the thrill of cosmic exploration. The universe always has another surprise waiting in the dark. Recent observations suggest something even more startling about this cosmic void. It may not just sit there in the darkness, but actively stretch wider over time. Think of it like a crack in the foundation of the universe, slowly spreading under forces we can't yet see. If proven true, this expansion could upend what we know about dark energy, that mysterious force pushing the cosmos apart at an accelerating rate. Right now, scientists assume dark energy works uniformly across space, like an invisible tide lifting all galaxies equally. But if voids like this are growing faster than expected, it might mean dark energy isn't behaving the way we thought. Perhaps it's stronger in these empty regions or interacting with structures in ways our models never predicted. One clue comes from the void's gravitational footprint. As it expands, it tugs on surrounding matter with surprising strength, creating ripples in the cosmic web that connects galaxies. These ripples don't match simulations based on standard cosmology, like finding footsteps where no one should be walking. Some researchers suggest this could point to an unknown property of dark energy, one that grows more potent in emptiness. Others propose we're seeing the aftermath of a cosmic tug-of-war. The void's growth might be fueled by repulsive gravity, a theoretical phenomenon where extremely low-density regions effectively push matter away instead of pulling it in. Then there's the inflation connection. Cosmic inflation, the universe's explosive expansion in its first fraction of a second, could have planted the seeds for voids like this. Quantum fluctuations during that era might have created pockets of unbalanced energy, some denser than others. Over billions of years, the underdense regions ballooned into vast voids, while the overdense ones collapsed into galaxy clusters. But if the void is still expanding today, it raises a provocative question. Did inflation truly end, or are its echoes still shaping the cosmos in ways we're only now detecting? The implications are profound. If voids grow faster than the universe itself, they could eventually dominate its structure, leaving islands of matter isolated in an ever-darkening sea. This wouldn't just change our maps of the cosmos, it would alter its destiny. Current projections suggest a cold death scenario where expansion stretches matter so thin that stars can no longer form. But an accelerating void phenomenon might rewrite that timeline, hinting at a future even more extreme, one where emptiness itself becomes the universe's defining feature. What makes this hypothesis so gripping is how it ties into humanity's oldest questions. Are we seeing the fingerprints of forces beyond our current physics? Could the void's expansion be a message from another universe, or evidence that our cosmic neighborhood is far stranger than we imagined? Every telescope pointed at this enigma brings us closer to answers, but for now, the void keeps its secrets, stretching silently at the edge of everything we know. Dark energy might hold the key to understanding why this cosmic void isn't just sitting still. It could be actively stretching the fabric of space itself. Picture this: in regions packed with galaxies, gravity acts like an anchor, slowing down the universe's expansion. But in the emptiness of the void, there's hardly any matter to resist dark energy's push. It's like trying to hold back a tidal wave with a handful of sand. Dark energy wins, and space stretches faster here than anywhere else. This imbalance could explain why the void appears to be growing, as if the universe's seams are unraveling in this particular spot. The strangest part, dark energy was supposed to be uniform, a constant force evenly distributed across the cosmos. But if it's stronger in voids, that challenges everything we thought we knew. Imagine turning on a fan and expecting a gentle breeze, only to discover it blasts hurricane-force winds in certain corners of the room. That's the kind of puzzle scientists are facing. Some theories suggest dark energy isn't a single, simple force, but something more dynamic, a field that fluctuates based on the density of its surroundings. In crowded galactic neighborhoods, it might act subdued, but in the void's emptiness, it could run wild, accelerating expansion to extremes we've never seen before. This idea isn't just speculative, it's backed by subtle clues in the cosmic microwave background, the afterglow of the Big Bang. Tiny temperature variations in this ancient light hint that dark energy's effects might vary depending on where you look. If confirmed, it would mean the universe doesn't play by the same rules everywhere. Some corners might stretch faster, others slower, as if space-time itself has regional dialect. But here's where it gets even weirder. If dark energy truly dominates in voids, it could mean these empty regions are the universe's future. As galaxies drift farther apart, the voids between them will merge, creating ever larger deserts of nothingness. Over trillions of years, the cosmos might become a sparse network of isolated galaxy clusters, each separated by unimaginable gulfs of expanding darkness. It's a chilling thought. The voids we see today could be previews of the universe's final act, where emptiness becomes the default state of existence. Yet for all its mystery, dark energy's connection to the void offers a rare opportunity. By studying how space behaves in these extreme environments, scientists might finally crack one of cosmology's toughest nuts: what dark energy actually is. Is it a property of space itself, or something more exotic, like a particle we've yet to discover? The void, with its eerie silence and inexplicable growth, could be the laboratory we need to find out. Every measurement, every observation brings us closer to answers, or to even bigger questions we haven't thought to ask yet. The cosmic microwave background is like a time capsule, a snapshot of the universe when it was just 380,000 years old, its faint glow carrying secrets from the dawn of time. And right there, etched into this ancient light, lies the void's ghostly signature. Scientists first noticed it as a peculiar cold spot, a patch of the sky where the CMB's temperature dips slightly lower than expected. At first glance, it might seem insignificant, a tiny fluctuation in a sea of microwave static. But this subtle chill could be the key to unraveling one of cosmology's greatest mysteries. Here's why it matters. When light travels through space, it interacts with the matter and energy in its path. Normally, photons from the CMB gain a tiny burst of energy as they pass through galaxy clusters, pulled by gravity's grip, a phenomenon called the sachs-wolfe effect. But when those same photons cross an enormous void, something bizarre happens. Instead of gaining energy, they lose it, like a ball rolling uphill against gravity's pull. The result, a colder patch in the CMB, a cosmic shadow cast by the void's emptiness. This isn't just a theoretical quirk, it's been measured. The cold spot aligns almost perfectly with the Eridanus Supervoid, as if the universe left us a breadcrumb trail to follow. But the plot thickens. Some researchers argue the cold spot is too extreme to be explained by the void alone. The temperature drop is larger than our models predict, suggesting there's more to the story. One daring hypothesis proposes that the cold spot might be evidence of a cosmic texture, a defect in spacetime itself, left over from the universe's violent birth. Think of it like a wrinkle in a bedsheet, frozen into the fabric of reality during the Big Bang's chaotic aftermath. If true, this would mean we're not just looking at an empty region of space, but a fossilized relic of the universe's first moments. Then there's the multiverse angle. Could the cold spot be a bruise from a collision with another universe? In theories where our cosmos is one bubble among many, such collisions would leave behind distinct patterns in the CMB anomalies that don't fit the standard cosmic recipe. The void's cold spot happens to match the kind of signature these models predict. It's as if we've found a fingerprint on the windowpane of reality, hinting at something vast and unseen beyond. What makes these CMB clues so powerful is their universality. Unlike distant galaxies or fleeting cosmic events, the microwave background is everywhere, a backdrop against which all structures, including the void, are silhouetted. By mapping its subtle ripples with missions like Planck and the upcoming Simons Observatory, scientists are piecing together a story written in the faintest whispers of heat and cold. Each new dataset sharpens the image, revealing whether the void is a solitary anomaly or a signpost to deeper truths. One thing's certain, the CMB isn't just a relic of the past. It's a living puzzle, a codebook waiting to be cracked. And as we decode its patterns, we might finally answer whether the void is a cosmic accident or a message from the universe itself, written in the language of primordial light. Deep within the cosmic microwave background's faint glow lies a puzzle that refuses to be ignored, a cold spot so pronounced it defies easy explanation. Stretching across a patch of sky 5 times wider than the full moon, this region isn't just slightly cooler than its surroundings. It's a deep freeze in the universe's thermal fabric, standing out like an ice crystal on a warm windowpane. At first glance, it might seem like a statistical fluke, a random blip in the data. But when astronomers realize this chilly anomaly aligns almost perfectly with the Eridanus Supervoid, the implications became impossible to dismiss. Here's where the science gets thrilling. When light from the CMB travels through the void's emptiness, it experiences a phenomenon called the integrated sachs-wolfe effect. Normally, photons climbing out of a galaxy cluster's gravitational well lose energy, appearing slightly cooler, a well-understood process, but in the void's case, the opposite happens. Photons entering this vast emptiness actually lose energy as they traverse it, like a hiker expending extra effort crossing a desert with no landmarks to gauge progress. The result, a cold spot in the CMB that mirrors the void's staggering scale. Yet there's a catch: the cold spot's temperature drop is more extreme than the void alone should produce. It's as if the universe handed us a receipt with an unexplained charge, leaving scientists scrambling to balance the cosmic books. One radical theory suggests the cold spot might not be caused by the void at all, but by something far stranger, a cosmic texture. These hypothetical structures are thought to be defects in spacetime itself, wrinkles left over from the universe's rapid expansion in its infancy. Like a knot frozen in a stretched rubber sheet, a texture could distort light in ways that mimic a cold spot, offering an alternative explanation that doesn't rely on the void's influence. Then there's the multiverse angle. If our universe collided with another in the distant past, the energy released could have created both the void and its associated cold spot, a cosmic bruise marking the point of impact. Simulations of such collisions produce cold spots eerily similar to the one we observe, complete with subtle asymmetries in their shape. It's as if we're staring at a bullet hole in the fabric of reality, with the void acting as the exit wound. What makes this mystery so compelling is how it ties into broader questions about the universe's structure. If the cold spot truly is the void's fingerprint, it reinforces the idea that emptiness can shape the cosmos as powerfully as matter. But if it's evidence of a texture or multiverse collision, it opens doors to physics beyond our current understanding. Every new observation, from next-generation CMB telescopes to ultra-deep galaxy surveys, brings us closer to an answer, or to a deeper question we haven't even thought to ask. For now, the cold spot remains a tantalizing enigma, a whisper from the edge of the known universe that refuses to be ignored. The universe isn't a smooth, evenly mixed soup of matter. It's more like a sponge riddled with holes. Most of those holes are small, at least by cosmic standards, where voids span a few 100 million light-years between strands of the cosmic web. But the Eridanus Supervoid isn't just another gap in the structure. It's a cosmic Grand Canyon, dwarfing everything around it. To understand why it's such an outlier, we need to rewind time and watch how the universe built itself. Imagine the cosmos in its youth, when matter was spread nearly evenly, like flour dusted over a table. Tiny quantum fluctuations from the Big Bang created slight variations. Some areas had a bit more matter, others a bit less. Over billions of years, gravity amplified those differences. The denser regions pulled in more material, growing into galaxy clusters and the glowing filaments of the cosmic web. The sparser regions, meanwhile, lost out. As matter drained away, they expanded into voids. Typical voids are part of this balanced ecosystem. They're not true emptiness, just neighborhoods with fewer galaxies. But the Eridanus Supervoid is different. It's not merely underdense, it's a near-perfect vacuum on a scale that shouldn't exist. If the cosmic web is a network of bustling cities connected by highways, this void is an entire continent left untouched. The question isn't just how it formed, but why it didn't get filled in like all the others. One clue lies in its age. Some simulations suggest this void could be a relic from the universe's first moments, a bubble of lower density frozen in time. While most regions were busy clumping into galaxies, this one stayed stubbornly empty, as if it missed the memo. Another theory points to dark energy's role. the repulsive force accelerating the universe's expansion might work overtime in voids, pushing matter away faster than gravity can pull it back. But here's the twist: the cosmic web isn't static. It's a dynamic, evolving structure with voids growing larger as the universe expands. Smaller voids merge like soap bubbles, creating ever larger empty regions. The Eridanus Supervoid might be a preview of the far future, when the cosmic web stretches thin and voids dominate the cosmos. What makes this contrast so fascinating is what it reveals about the universe's personality. It's not a machine running on fixed rules. It's a place of wild variation, where chance and physics intertwine to create structures that defy expectations. The cosmic web is the universe's backbone, but voids like Eridanus are its unanswered questions, reminding us that for all we've learned, the cosmos still holds mysteries too big to ignore. To grasp how quantum fluctuations could birth something as colossal as the Eridanus Supervoid, we need to shrink down to the smallest scales imaginable, and then watch the universe explode. Picture the cosmos in its first sliver of a second, a seething, hot soup of energy where the rules of quantum mechanics reign. Here, particles flicker in and out of existence, dancing in a chaotic storm of uncertainty. These aren't just tiny blips, they're the universe's first brushstrokes, random ripples in spacetime that would one day shape everything from stars to supervoids. In those frenzied moments, something extraordinary happened. The universe underwent inflation, expanding faster than light itself, stretching those quantum ripples from microscopic to cosmic scales. Imagine blowing up a balloon with tiny wrinkles on its surface. As it inflates, those wrinkles grow into vast creases. That's essentially what occurred during inflation, but with space-time itself. Regions that started slightly denser became galaxy clusters. Regions slightly emptier stretched into voids. The Eridanus Supervoid might be one of those primordial wrinkles, a quantum hiccup frozen in time and blown up to staggering proportions. But here's where it gets even stranger. Quantum fluctuations are random by nature, which means the void might not be a rare outlier. It could be inevitable. In an infinite universe, probability dictates that some regions would end up far emptier than others, simply by chance. It's like rolling a cosmic die trillions of times. Eventually, you'll land on a sequence so unlikely it defies expectation. The void could be that statistical extreme, a 1 in a quintillion roll of the quantum dice. Yet not all scientists are convinced randomness alone explains it. Some theories suggest these fluctuations weren't entirely chaotic. They might have been shaped by hidden forces or fields we haven't yet discovered. For instance, certain models of dark energy predicted could have interacted with quantum fields during inflation, amplifying some fluctuations while suppressing others. If true, the void isn't just a frozen accident, it's a deliberate signature, a message from the universe's birth encoded in emptiness. What makes this idea so compelling is how it bridges the unimaginably small with the astronomically large. The same quantum rules governing particles in a lab could have sculpted the vast cosmic structures we see today. It's as if the universe left us a trail of breadcrumbs, starting with subatomic flickers and ending with a billion light-year abyss. And if we can decode that trail, we might uncover secrets not just about the void, but about the quantum fabric of reality itself. The implications ripple outward. If quantum fluctuations really did seed the void, it challenges our assumptions about how structure forms in the cosmos. We've long assumed galaxies and clusters were the universe's primary architecture, with voids as afterthoughts. But what if emptiness is just as fundamental? It's like realizing the holes in Swiss cheese aren't gaps in the structure, they're part of the recipe. This perspective flips cosmology on its head, suggesting the universe's grand design might be as much about absence as presence. There's another tantalizing possibility. The void might not be unique. If quantum fluctuations created one, they could have created others, perhaps even larger, stranger voids lurking beyond our observational horizon. Future telescopes like the Vera Rubin Observatory or the James Webb's Deep Field Surveys might uncover more of these cosmic ghosts, revealing whether the Eridanus Supervoid is a solitary anomaly or part of a hidden pattern. For now, the void stands as a monument to quantum uncertainty writ large. It reminds us that the universe's blueprint was drawn in randomness, its grandest structures born from the tiniest tremors. And as we peer into its depths, we're not just studying emptiness, we're staring back in time, witnessing the aftermath of a quantum whisper that echoed across 13.8 billion years. Imagine our universe as a soap bubble floating in an infinite cosmic froth, one among countless others, each with its own laws of physics and dimensions beyond our perception. This is the multiverse theory, and if it's true, the void at the edge of our universe might not just be emptiness, it could be a scar from a collision with another reality. Think of it like two balloons pressed together. Where they meet, the rubber stretches thin, leaving behind a distorted mark. That's what some scientists believe the Eridanus Supervoid represents, a cosmic fingerprint from a long-ago encounter with a universe we'll never see. The idea isn't as far-fetched as it sounds. When physicists model how bubble universes might interact in a multiverse, they find that collisions would create distinct patterns, regions of space stretched thin or emptied out, like wrinkles in spacetime. These wouldn't look like ordinary voids. They'd be sharper, colder, and more asymmetrical, matching the bizarre profile of the Eridanus Supervoid. Even stranger, the cold spot in the cosmic microwave background aligns eerily well with predictions for such an impact, like a bruise lingering on the skin of our cosmos. But how could we ever prove this? The challenge lies in ruling out more mundane explanations. For instance, cosmic inflation. The universe's explosive early growth could have created similar voids through quantum fluctuations. The difference is in the details. A collision scar would leave behind subtle imprints in the polarization of the CMB, a specific twist in the ancient light that inflation alone can't explain. Future telescopes like the Simons Observatory are hunting for these fingerprints right now, scanning the sky for clues written in the universe's oldest light. What makes this theory so electrifying is its implications. If the void really is a collision mark, it means we're not just mapping our universe, we're glimpsing the contours of others. It's like finding a seashell on a mountaintop, evidence of forces far greater than the landscape we know. Even if the multiverse remains unproven, the void forces us to ask, what else might be lurking beyond the edges of our cosmic map? The answer could rewrite not just cosmology, but our very understanding of reality itself. Not every cosmic mystery comes with unanimous agreement. Science thrives on healthy skepticism, and the Eridanus Supervoid is no exception. While some researchers see it as a groundbreaking anomaly, others aren't convinced it's anything more than a cosmic mirage. One camp argues that the void might just be a statistical outlier, a random fluctuation in the distribution of matter that only looks significant because of the sheer scale of our observations. Imagine rolling a die 1,000,000 times eventually. You'll get a sequence that seems impossibly rare, even if it's just chance. Could the void be the universe's version of that unlikely roll? Then there's the question of measurement. Mapping something 1,000,000,000 light years across isn't like surveying a city block. It's an exercise in piecing together indirect clues. Some astronomers suggest that what we're calling a supervoid might actually be several smaller voids lined up along our line of sight, creating the illusion of a single colossal structure. It's like mistaking a chain of islands for a single continent when viewed from afar. If true, the void's apparent size and impact could be overestimated, turning a curiosity into a false paradigm. But the most heated debate centers on the cold spot in the cosmic microwave background. Skeptics point out that the temperature dip isn't perfectly aligned with the void's center, and the math doesn't quite add up. The void's predicted effect on the CMB is weaker than what we observe. This mismatch has led some to propose that the cold spot might be unrelated, a random fluctuation in the primordial light itself. Others go further, suggesting that our tools for analyzing the CMB could be subtly biased, like a camera lens that distorts colors without us realizing it. What makes this debate so valuable is how it reflects the self-correcting nature of science. Extraordinary claims require extraordinary evidence, and the void's proponents are racing to gather more data. New surveys, like those from the Dark Energy Spectroscopic Instrument, are mapping the distribution of galaxies with unprecedented precision, while next-generation CMB experiments aim to scrutinize the cold spot down to microkelvin variations. The goal isn't just to prove who's right, it's to refine our understanding of the universe, whether the void stands as a landmark or fades into statistical noise. At its core, this isn't just about one enigmatic patch of space. It's a reminder that cosmology is a living, evolving field, where even the strangest discoveries must survive the gauntlet of doubt. And that's how we inch closer to the truth, by questioning everything, especially the things that seem too extraordinary to be real. The next generation of telescopes is gearing up to turn the void from a cosmic curiosity into a testing ground for fundamental physics. Leading the charge is the James Webb Space Telescope, with its infrared eyes peeled for the faintest traces of light distorted by the void's immense gravity. Unlike optical telescopes that see only visible starlight, Webb's instruments can detect the heat signatures of galaxies hidden behind the void's emptiness, galaxies whose light has been stretched and warped by billions of years of cosmic expansion. It's like using thermal goggles to spot campfires through fog. Where previous surveys saw only darkness, Webb might reveal the void's true structure in unprecedented detail. Meanwhile, the Euclid mission takes a different approach. Launching with the sole purpose of mapping dark energy's influence, this space telescope will chart the void's growth over time by measuring how its gravitational field bends light from distant galaxies. Imagine drawing a grid on a rubber sheet, then watching how the squares distort as someone stretches the fabric beneath. That's essentially what Euclid will do on a cosmic scale. By tracking subtle changes in the void's shape and depth, scientists hope to catch dark energy in the act, revealing whether it truly behaves differently in these empty regions. But the real game changer could come from combining these datasets. When Webb's galaxy surveys overlap with Euclid's dark energy maps, researchers will create the most comprehensive 3D model of the void ever assembled. They'll be able to see not just where matter is missing, but how the void's expansion warps spacetime around it, like reconstructing an invisible whirlpool by watching how debris floats past. This could settle once and for all whether the void is a statistical fluke or a sign of deeper physics at work. The stakes couldn't be higher. If these missions confirm the void's expansion defies standard cosmology, it might force us to rewrite textbooks on dark energy. Some theories predict Webb could find galaxies distributed in patterns that suggest repulsive gravity within the void, while Euclid might detect expansion rates that vary like cosmic weather patterns rather than following uniform laws. Either discovery would send shockwaves through astrophysics, potentially upending our understanding of how the universe grows and evolves. Yet the most exciting possibility isn't confirming existing theories, it's discovering something entirely unexpected. History shows that whenever we build telescopes capable of seeing farther and sharper, the universe reveals surprises we never imagined. The void, with its eerie silence and unexplained behavior, might be hiding clues to phenomena we haven't even hypothesized yet. As these next-generation instruments come online, they're not just answering questions, they're teaching us what questions we should be asking. To understand the void, scientists are building entire universes from scratch, not in labs but inside supercomputers. These aren't just simple models, they're staggeringly complex simulations that recreate the cosmos down to the gravitational tug of individual galaxies. By programming virtual universes with different physics, some with standard dark energy, others with exotic multiverse collisions or modified gravity, researchers can watch how voids like Eridanus might form over billions of years. It's like running a cosmic time-lapse where every parameter can be tweaked to test which theories match the real void's eerie profile. One groundbreaking simulation, run on Oak Ridge National Laboratory's Frontier supercomputer, recreated a volume of space over 300 million light-years wide. The team seeded it with quantum fluctuations mirroring those from the Big Bang, then hit play to watch structures emerge. In some runs, typical voids formed patchy but unremarkable. But in others, when they dialed up inflation's initial randomness, colossal supervoids appeared, eerily similar to Eridanus. The key difference: these virtual voids often had sharper edges and more asymmetrical shapes, hinting that our real-world void might indeed be a relic of extreme early universe conditions. Yet simulations also reveal surprises. When scientists added repulsive gravity to voids, a theoretical tweak where emptiness pushes matter away, their models produced cold spots in the simulated cosmic microwave background that matched observations almost perfectly. This wasn't just a numerical coincidence. It suggested the void's influence on light might be more complex than we thought. Other teams testing multiverse collision scenarios found these events could leave behind void-like structures, but with distinct gravitational wave patterns we might someday detect. The real power of these simulations lies in their predictive ability. By comparing virtual voids to the real one's exact dimensions, density, and gravitational effects, researchers can rule out theories that don't fit. For instance, if a simulation assuming uniform dark energy can't produce a void as large and cold as Eridanus, that's a strike against the standard model. It's like solving a murder mystery by recreating the crime scene, except here, the suspects are alternate physics, and the victim is our conventional understanding of the cosmos. What makes this approach so revolutionary is how it transforms abstract math into visible cosmic history. We can't rewind the real universe, but in these digital realms, we can watch a supervoid's life story unfold from first quantum flicker to its present-day expanse. And as supercomputers grow more powerful, these simulations will inch closer to reality, potentially revealing whether the Eridanus supervoid is a cosmic accident or a signpost to physics we've yet to discover. Light doesn't just travel through the void, it tells its story. As photons from the cosmic microwave background journey across this billion light-year emptiness, they don't emerge unchanged. The void's gravitational grip, or rather its lack thereof, leaves a ghostly fingerprint on the light itself, a phenomenon known as the integrated sachs-wolfe effect. Here's how it works. Imagine a hiker trekking through a mountain range. Climbing uphill, they burn energy. Descending, they regain it. Light behaves similarly when passing through galaxy clusters, gaining energy as it enters their gravitational wells and losing it as it exits. But the void flips this script. Instead of a mountain, it's a vast, flat desert. Photons entering this emptiness expend energy struggling against the void's weaker gravity, like a cyclist pedaling harder when the road turns to sand. By the time they exit, they're slightly depleted, their wavelength stretched cooler than when they began. This energy loss isn't theoretical. It's etched into the cosmic microwave background as a distinct cold spot, a patch of sky where the CMB's temperature dips just a few millionths of a degree. That might sound negligible, but in cosmology, such tiny deviations scream volumes. The alignment between this cold spot and the Eridanus Supervoid is like finding a fingerprint at a crime scene. It places the void squarely in the narrative of cosmic history. Yet the plot thickens. The cold spot's temperature drop is more dramatic than standard models predict, as if the void's emptiness exerts a stranger pull than gravity alone can explain. Some theorists suggest this discrepancy hints at unseen forces, perhaps dark energy behaving differently in voids, or even spacetime itself warping in ways Einstein's equations didn't anticipate. It's as if the void isn't just empty space, but a lens distorting light through hidden physics. What makes this interaction so extraordinary is its reversibility. While galaxy clusters leave sharp imprints on light, voids create subtler, more diffuse shadows, their effects only detectable when averaged over colossal scales. Spotting them requires comparing maps of galaxy distribution with painstakingly detailed CMB temperature readings, a cosmic matchmaking effort that took decades to perfect. The payoff: proof that emptiness isn't passive. It bends light, sculpts spacetime, and whispers secrets about the universe's structure in a language we're only beginning to decode. This ghostly interplay between light and void doesn't just confirm the Eridanus Supervoid's existence, it turns it into a laboratory. By studying how photons lose energy here, scientists can probe dark energy's influence in environments where matter doesn't dominate. It's like testing wind resistance not in a forest, but in open air, revealing forces that crowded galactic neighborhoods might obscure. Every photon that traverses the void carries a message. The universe's emptiest places might hold the keys to its deepest mysteries. Black holes aren't just cosmic vacuum cleaners, they might also be architects of emptiness. While the Eridanus Supervoid scale makes it unlikely to be the work of black holes alone, these gravitational behemoths could still hold clues about how vast regions of space get cleared out over time. Picture a supermassive black hole at the center of a galaxy, its immense gravity tugging on everything nearby. Over billions of years, its influence can fling stars and gas outward like a slingshot, gradually carving out a bubble of relative emptiness. Now imagine this process playing out across countless galaxies, with black holes collectively pushing matter toward the edges of their cosmic neighborhoods. The result, a patchwork of smaller voids that, under the right conditions, might merge into something larger. But here's the catch: even the most voracious black holes can't account for the Eridanus Supervoid's staggering size. To create a void 1.8 billion light-years across, you'd need a mechanism far more extreme than scattered black holes clearing out their corners of the universe. That's where things get interesting. Some theorists propose that black holes might still play an indirect role, not by emptying space themselves, but by shaping the large-scale structure that allows voids to form. For example, the energy released by colliding supermassive black holes could send shockwaves through intergalactic gas, preventing it from collapsing into new galaxies and leaving behind underdense regions. It's like dropping a stone in a pond and watching the ripples push floating leaves to the edges, leaving the center eerily still. Then there's the dark matter connection. Black holes are thought to form in the densest knots of dark matter, the invisible scaffolding of the cosmos. If dark matter's distribution is patchy, with some regions unusually sparse, it could create natural voids where galaxies rarely form. Black holes in this scenario would be symptoms of the underlying structure, not its cause. They'd mark the spots where matter clustered, while the voids would be the shadows cast by the universe's missing scaffolding. What makes this idea so compelling is how it ties into the broader story of cosmic evolution. Voids and black holes might seem like opposites, one an absence, the other an overabundance of gravity, but they're part of the same dynamic system. Just as forests need clearings to thrive, the cosmic web needs voids to balance its dense clusters and filaments. And if black holes help maintain that balance, even in small ways, they're not just destroyers, they're cosmic gardeners, shaping the universe's emptiness as surely as its light. The Eridanus Supervoid may dwarf anything black holes could create, but studying their influence on smaller voids could reveal hidden patterns in how the universe organizes itself. After all, the biggest mysteries often start with the smallest clues. Some theories about the void venture far beyond conventional physics into realms where spacetime itself might be flawed. One radical proposal suggests the Eridanus Supervoid isn't just an empty region, but a cosmic defect, a tear in the fabric of reality left over from the universe's birth. Picture the early cosmos as molten glass cooling rapidly. If the process wasn't perfectly even, cracks could have formed, freezing into place as the universe expanded. These hypothetical cosmic textures would distort space around them, creating regions where gravity behaves oddly and light stretches in unexpected ways. The void's alignment with the CMB cold spot fits this idea eerily well, like a fingerprint matching a suspect's hand. Then there's the pre-Big Bang scenario. Could the void be a relic from a time before time? Some models of quantum gravity suggest our universe emerged from the collapse of a previous cosmos, a cyclical rebirth where echoes of the old universe lingered. In this view, the void might be a scar from that cataclysm, a pocket of distorted spacetime that survived the reset. It's like finding a fossilized tree ring in a younger forest, evidence of a world that existed before this one. Even wilder is the holographic principle, which posits our three-dimensional universe might be a projection from a two-dimensional boundary. If true, the void could represent a glitch in that cosmic code, a pixelation error on the grandest scale. Think of a scratched DVD where part of the movie skips. The void might be spacetime's version of that skip, a region where the data of reality didn't render correctly. What ties these theories together is their audacity. They don't just tweak existing physics, they rewrite the rules entirely, yet they're not pure speculation. Each makes testable predictions, from subtle gravitational anomalies to patterns in the cosmic microwave background that upcoming telescopes could detect. The void, in this light, becomes more than a curiosity. It's a battleground for competing visions of reality, where the stakes are nothing less than understanding the universe's true nature. The most humbling part, these ideas might all be wrong. But that's the beauty of cosmic mysteries. They force us to question not just what we know, but how we know it. Whether the void is a texture, a relic, or something beyond our current imagination, its existence proves the universe still has stories to tell that we're only beginning to decipher. The Eridanus Supervoid has inspired wild theories from interdimensional gateways to alien engineering on a galactic scale. While these ideas make for gripping sci-fi, the truth is both simpler and far more fascinating. The void isn't a constructed anomaly or a tear in reality. It's a natural consequence of the universe's messy, uneven growth. Think of it like weather patterns on Earth. Just as some regions end up drier or stormier due to complex atmospheric dynamics, the cosmos develops pockets of extreme density and extreme emptiness through the interplay of gravity, dark energy, and chance. One persistent myth paints the void as a doorway to other dimensions, fueled by its eerie darkness and incomprehensible scale. But in reality, it's no more mysterious than the gaps between threads in a spiderweb. The void's emptiness isn't a glitch, it's a feature of the cosmic web's design. where matter clusters into filaments and leaves vast, bubble-like voids between them. What makes Eridanus special isn't supernatural origins, but its size. It's the Grand Canyon of voids, a record holder that pushes the limits of what we thought possible, not a breach in the laws of physics. Then there's the alien megastructure trope, the idea that advanced civilizations might have somehow cleared this region of space. While it's fun to imagine a Kardashev Type 3 civilization at work, the numbers don't add up. Even if every star in the Milky Way were dismantled for construction, it wouldn't make a dent in a volume spanning billions of light years. Nature doesn't need aliens to create emptiness. It's been doing so since the Big Bang, with quantum fluctuations and dark energy as its tools. The real danger of these misconceptions isn't just inaccuracy, it's the missed opportunity to appreciate the void for what it truly represents, a laboratory for testing the universe's fundamental rules. By framing it as a cosmic oddity rather than a natural extreme, we overlook how voids shape galaxy formation, influence dark energy's behavior, and even leave fingerprints on the oldest light in existence. They're not exceptions to the cosmic order, they're integral to it, like the silent pauses between musical notes that give the symphony its rhythm. What's remarkable is how the void's true story outshines the myths. A natural phenomenon of this scale, born from quantum seeds and stretched across eons, challenges our understanding far more profoundly than any sci-fi portal. It forces us to confront how little we grasp about the universe's architecture and how much remains to be discovered in the spaces between everything. The void doesn't just challenge our understanding of physics, it unsettles something deeper. Staring into its emptiness, we're forced to grapple with a universe that might not just fade, but actively unravel. Consider this: if voids like Eridanus keep expanding, their hunger could one day outpace the cosmos itself. Galaxies, those glittering islands of stars and life, would find themselves isolated in ever-growing oceans of darkness, their light stretched too thin to bridge the gaps. It's a future where the cosmic web doesn't just thin, it tears apart strand by strand until every civilization, every planet, every atom is alone in the infinite black. This isn't just speculative astronomy, it's a mirror held up to our own fragility. Human history spans a mere blink against the cosmos timeline, yet we've built myths and meaning on the assumption that the stars will always be there to guide us. The void whispers a different story, one where time, not space, is the ultimate frontier. If emptiness grows dominant, the universe could face a fate colder than heat death, a void death, where structure dissolves not from decay but from dilution. Imagine pouring ink into an expanding pool. No matter how vivid the color, it eventually fades to nothing. Yet there's a paradoxical beauty in this bleak vision. The void's expansion forces us to ask why any of this matters. If galaxies are destined for isolation, does our search for connection, for signals from other civilizations, for understanding our place in the cosmos become more urgent or more futile? Philosophers have wrestled with such questions for millennia, but the void makes them visceral. It's no longer abstract musing. It's written into the fabric of reality, a reminder that the universe owes us neither permanence nor meaning. But here's the twist: the void might also be the universe's greatest teacher. Its emptiness highlights what we so often overlook, that existence, however fleeting, is a statistical miracle. Against the backdrop of infinite nothingness, the fact that we're here at all, gazing into the abyss and daring to comprehend it, becomes a rebellion against indifference. The void doesn't just threaten, it clarifies. It strips away cosmic distractions, leaving only the essential question: what do we do with the time and space we've been given? Perhaps that's the most profound lesson hidden in the darkness. the universe's impermanence isn't a flaw, it's the very condition that makes our moment meaningful. Stars burn out, galaxies drift apart, and voids may one day dominate, but here and now, we're witnesses to a cosmos rich with wonder. The void's expansion isn't just an astronomical phenomenon. It's a call to look upward while we still can, to marvel at the light before the darkness takes its turn. The Eridanus Supervoid may be colossal, but it's not the universe's only great emptiness. Scattered across the cosmos are other vast voids, each with its own peculiarities, like the Boötes Void, a spherical abyss spanning 330 million light-years. At first glance, these cosmic deserts might seem similar, but their differences tell a story about how the universe builds and unbuilds its grandest structures. Take Boötes, often nicknamed the Great Nothing. While Eridanus stretches like a flattened bubble, Boötes is remarkably round, as if someone punched a perfect sphere from the cosmic web. Its emptiness is also more extreme. Where Eridanus contains a handful of dim galaxies, Boötes holds only 60 or so in a volume that should host thousands. This makes Boötes less a void and more a true desert, a place where matter didn't just thin out, but nearly vanished altogether. Then there's the local void, right in our galactic backyard. Unlike Eridanus or Boötes, this void isn't entirely empty. Our Milky Way actually borders it, and its gravitational push may be subtly nudging our galaxy through space. Imagine living near a quiet forest that's slowly being abandoned. The local void is like that forest, with galaxies trickling away over eons, leaving behind growing pockets of stillness. What's fascinating is how these voids form. While Eridanus might be a relic of quantum fluctuations from the Big Bang, Boötes could be the aftermath of multiple smaller voids merging, like soap bubbles combining into a larger one. The local void, meanwhile, might owe its existence to dark energies push overcoming gravity's pull in our corner of the cosmos. These differing origins hint that emptiness isn't a single phenomenon, it's a spectrum shaped by the universe's chaotic growth. Size isn't the only variable. Voids also differ in their edges. Some, like Eridanus, have fuzzy boundaries where galaxies gradually thin out. Others, particularly those in dense regions of the cosmic web, can have shockingly sharp borders, almost as if matter hit an invisible wall. These contrasts suggest that voids aren't passive absences, but active players in shaping the universe's structure. The real surprise, voids might be the universe's most common feature. Recent surveys suggest they make up about 80% of the cosmos's volume, with galaxies confined to the remaining 20% like decorations on a vast, invisible scaffold. That means the universe isn't primarily a collection of stars and galaxies, it's a sea of emptiness, dotted with occasional islands of light. By comparing voids, cosmologists are piecing together a surprising truth. The universe's structure depends as much on what's missing as what's present. The Eridanus Supervoid isn't an anomaly, it's part of a pattern, one that's still emerging as we map the cosmos's silent expanses. And with each new void we discover, the pattern grows clearer, revealing a universe built not just by gravity's pull, but by emptiness's push. The growing emptiness of the Eridanus Supervoid might be more than just a cosmic curiosity. It could be a preview of the universe's most violent possible fate. Enter the Big Rip, a theoretical scenario where dark energy doesn't just accelerate the universe's expansion, but grows infinitely stronger over time, eventually tearing spacetime itself apart. Picture this: galaxies first drift farther apart, then star systems are ripped from their orbits, planets shredded from their suns, and finally, atoms themselves are pulled asunder. It's not just the end of matter, it's the unraveling of reality's very fabric, and the void's accelerating expansion hints that this apocalyptic finale might not be as far-fetched as it sounds. What makes the Big Rip so chilling is its mechanism. Most models assume dark energy's strength remains constant, gently pushing galaxies apart. But if it's a more exotic form called phantom energy, its influence could grow exponentially, becoming overwhelming even on the smallest scales. The void offers a disturbing test case. Its apparent faster than expected growth aligns with predictions for how phantom energy would behave in low-density regions. It's like watching a crack in a dam widen first slowly, then with sudden catastrophic speed. Here's where the science gets counterintuitive. In a Big Rip scenario, voids wouldn't just expand, they'd merge, their emptiness becoming the dominant feature of the cosmos. Galaxies would be stranded like islands in an ever-rising sea, their gravity increasingly powerless against the tide. The Eridanus Supervoid, already a billion light-year chasm, could one day swallow entire galactic superclusters, its edges accelerating faster than light can cross the distance. By the time the final moments arrived, even the void itself would be torn apart, spacetime fracturing like thin ice under infinite pressure. Yet there's hope this nightmare scenario won't unfold. Current observations show dark energy's strength holding steady, with no evidence yet of the runaway amplification phantom energy requires. The void's expansion, while puzzling, might still fit within modified gravity theories or other less apocalyptic explanations. Some cosmologists argue that even if the Big Rip is possible, it wouldn't occur for hundreds of billions of years, far beyond the lifespan of stars or any conceivable civilization. What makes the void's connection to the Big Rip so compelling isn't just the science, it's the philosophical weight. This cosmic emptiness forces us to confront whether the universe's fate is one of quiet fading or violent dissolution. Most endings in nature are slow. Stars cool, black holes evaporate, entropy smooths all gradients. But the Big Rip is different, a crescendo of destruction that would leave no remnant, no fossil, not even empty space to mark what once was. The void, in this light, becomes both a warning and a challenge to understand dark energy's true nature before it's too late, if such an ending is even written in the cosmos's cards. Perhaps the most profound lesson lies in the timing. If the void is indeed a herald of the Big Rip, it's a reminder that the universe's grandest processes operate on timescales beyond human comprehension. Our entire species could rise, flourish, and vanish in the blink of a cosmic eye, leaving the void to continue its slow march toward whatever destiny awaits. And that's the paradox of studying such mysteries. They humble us with their scale, even as they inspire us to keep searching for answers in the darkness. For centuries, astronomers gazed at the night sky assuming the stars were scattered evenly across the cosmos like grains of sand sprinkled on a vast, dark shore. Ancient Greek thinkers envisioned a celestial sphere with uniform brilliance, while medieval scholars mapped the heavens as a flawless tapestry of fixed lights. Even when telescopes revealed the Milky Way's cloudy band was made of countless stars, the assumption persisted. Surely, if we could peer deep enough, we'd find stars filling every corner of space. That illusion shattered in the late 20th century when astronomers began mapping the universe in 3 dimensions. Instead of an even distribution, they found galaxies clustered in sprawling filaments and walls, separated by staggering voids, some so vast they could swallow thousands of Milky Ways without a trace. The first major clue came in 1981, when Harvard's Robert Kirshner and his team discovered the Boötes void, a spherical emptiness 330 million light-years wide containing just 60 galaxies where thousands should have been. It was like stumbling upon a desert in the middle of a rainforest, a place where the rules of cosmic geography seemed broken. This revelation didn't happen overnight. Early galaxy surveys in the 1970s hinted at uneven distribution, but without precise distance measurements, astronomers couldn't distinguish true voids from sparse regions. The breakthrough came with redshift surveys, which used the Doppler effect to calculate how fast galaxies were moving away from us, and thus their true positions in space. As these maps grew more detailed, a startling pattern emerged. The universe wasn't a starry soup, but a cosmic web, with galaxies threading along tendrils of dark matter and emptiness stretching between them. The paradigm shift was profound. Suddenly, the universe wasn't just expanding, it was structured, almost alive, with voids acting as engines shaping its evolution. Some astronomers resisted, arguing these holes might be observational errors or temporary features. But as surveys like the Sloan Digital Sky Survey mapped millions of galaxies, the evidence became undeniable. Voids weren't glitches, they were fundamental, occupying up to 80% of the cosmos's volume. What's fascinating is how this mirrors earlier scientific revolutions. Just as Copernicus showed Earth wasn't the center of the solar system, void discoveries proved galaxies weren't evenly scattered. They were trapped in a web whose empty spaces held their own secrets. Modern telescopes now study these voids not as absences, but as cosmic laboratories where dark energy's influence is magnified and gravity's rules might bend. From ancient myths of a star-studded firmament to our current view of a dynamic, bubbling cosmos, the story of voids reminds us that the universe always has another surprise waiting in the dark. The void isn't just a scientific curiosity, it's a canvas for the human imagination. From the pages of classic sci-fi to the immersive worlds of video games, this cosmic emptiness has inspired stories that range from chilling to transcendent. Take Arthur C. Clarke's Rendezvous with Rama, where a massive cylindrical void glides through our solar system, hiding secrets of an ancient alien civilization. Clarke's vision mirrors real astronomy in surprising ways, the idea that vast, mysterious structures could drift unseen until they're nearly upon us. Or consider Interstellar, where the black hole Gargantua's accretion disk gleams like a halo around abyssal darkness, a visual echo of how real voids warp light and time. These stories borrow from science but stretch it into myth, turning the void into a metaphor for the unknown itself. Gaming worlds take this even further. In No Man's Sky, players navigate a procedurally generated universe peppered with dead zones, regions where stars thin out and space turns eerily quiet. The game's algorithm mimics real galactic distribution so well that stumbling upon a virtual void feels uncannily like the real thing. Then there's Destiny 2, where the cosmic force known as the darkness manifests as literal voids swallowing planets whole. It's a dramatic exaggeration, but one rooted in humanity's primal fear of emptiness. The same dread that makes the Eridanus Supervoid so unsettling when scientists describe its scale. But pop culture doesn't always get it right. Some depictions, like Event Horizon's hellish void or Doctor Who's void ships, treat emptiness as a supernatural realm rather than a natural phenomenon. These creative liberties blur public understanding, leading to myths about voids being portals or alien constructs. Yet even these inaccuracies reveal something profound. The void taps into deep-seated human anxieties. It's the ultimate other, a place where physics feels optional and anything could lurk. What's fascinating is how art circles back to influence science. Concepts first imagined in fiction like multiverses colliding or spacetime defects now appear in legitimate theories about real cosmic voids. The line between inspiration and discovery grows thin, proving that sometimes to understand the universe, we first have to dream it. The pursuit of cosmic mysteries like the Eridanus Supervoid forces us to confront a fundamental dilemma. How much should humanity invest in unraveling the universe's secrets when urgent challenges plague our own planet? Consider this: the James Webb Space Telescope, one of our most powerful tools for studying the void, cost nearly $10 billion to build and launch. That same sum could fund global malaria eradication programs for years, build renewable energy infrastructure for millions, or provide clean water to countless communities. The question isn't whether the science is valuable, it's whether our resources are being spent where they matter most. This tension between earthly needs and celestial curiosity isn't new. When Galileo pointed his telescope at Jupiter's moons in 1609, critics argued he was wasting time while plagues ravaged Europe. Yet his discoveries laid the foundation for modern navigation, timekeeping, and even satellite technology. The same paradox applies today. Studying the void's expansion could revolutionize our understanding of dark energy knowledge that might one day unlock unimaginable energy sources or propulsion systems. The catch: these benefits are uncertain and decades away, while hunger, climate change, and inequality demand solutions now. Critics of big astronomy projects often frame it as an either-or choice, but the reality is more nuanced. Scientific funding doesn't operate like a fixed pie where one slice diminishes another. Many nations fund space research through dedicated budgets that wouldn't exist for humanitarian causes anyway. Moreover, the technological spin-offs from cosmic research like advanced imaging sensors, data compression algorithms, and radiation-resistant materials often trickle down to medical, environmental, and industrial applications. The microchips in your smartphone owe their existence to miniaturization efforts for space probes. Still, the ethical scales deserve careful balancing. While a child staring at Webb's images of the void might be inspired to become a scientist, another might wonder why we're mapping cosmic emptiness when their village lacks electricity. Perhaps the answer lies in redefining priorities rather than abandoning exploration. Some observatories now share telescope time between astronomers and climate scientists, using the same instruments to study atmospheric changes and distant galaxies. Others partner with engineers to adapt space-grade solar panels for affordable housing. What makes this debate so poignant is how it reflects our species' dual nature. We're creatures of immediate survival needs and boundless curiosity, of pragmatic problem-solving and existential wonder. The void represents more than a scientific puzzle. It's a mirror showing us who we are, beings torn between the dirt beneath our feet and the stars above, forever struggling to bridge the gap. In the end, the value of studying cosmic mysteries may not lie solely in their answers, but in how the questions shape us. A civilization that stops looking upward risks losing its sense of possibility, while one that ignores its suffering risks losing its soul. The challenge isn't choosing between Earth and the cosmos, it's learning to walk both paths without losing sight of either. Amateur astronomers with backyard telescopes might seem like unlikely players in the hunt for cosmic voids, but history proves otherwise. Some of the most groundbreaking discoveries in astronomy began with curious stargazers noticing anomalies that professional surveys overlooked. Take the case of Hanny's voorwerpen, a strange, glowing cloud of gas discovered in 2007 by Dutch schoolteacher Hanny van Arkel while she participated in the Galaxy Zoo project. Classifying galaxies online as a citizen scientist, she spotted an eerie blue smudge that turned out to be a quasar's ghostly echo, visible only because of its unique angle and timing. This discovery underscores a vital truth: the universe hides its secrets in plain sight, waiting for anyone with patience and passion to notice. Void research offers similar opportunities. While massive telescopes map the cosmos's large-scale structure, amateurs can contribute by monitoring subtle changes in galaxy distributions or identifying unusual patterns in star fields. Projects like the Cosmic Void Finder enlist volunteers to analyze data from the Sloan Digital Sky Survey, training algorithms to spot underdense regions that might hint at new voids. Others track redshift measurements of faint galaxies near known voids, helping scientists refine maps of these enigmatic regions. It's like crowdsourcing a cosmic treasure hunt, where every pair of eyes increases the chance of finding something extraordinary. The tools needed are more accessible than ever. A moderately priced telescope with a digital camera can capture images sharp enough for basic galaxy surveys, while free software like Aladdin's Sky Atlas lets anyone overlay their observations with professional datasets. Some amateurs even collaborate with researchers by monitoring voids over time, watching for gravitational lensing effects or unexpected light distortions that could reveal hidden mass. In 2019, a Japanese amateur astronomer using a 20-centimeter telescope detected a microlensing event near the Boötes Void, a fleeting alignment of stars that helped calibrate models of dark matter in the region. What makes this collaboration so powerful is its democratizing effect. Cosmic voids aren't just curiosities for elite institutions, they're puzzles anyone can help solve. When a retired engineer in Arizona logs galaxy positions or a high school student in Norway analyzes void boundaries, they're not just assisting professionals, they're reshaping our understanding of the universe's architecture. The next great void might not be found by a billion-dollar observatory, but by someone in their backyard staring at the sky and wondering what's missing. The beauty of amateur contributions lies in their unpredictability. Professionals design telescopes to test specific hypotheses, but amateurs often stumble into the unknown precisely because they're looking without preconceptions. It's how a British amateur discovered a new type of aurora-like phenomenon called Steve, and how a German astrophotographer captured the first clear images of a rare atmospheric flash called a blue jet. Voids, with their subtle influence on surrounding galaxies and light, are ripe for similar serendipity. This isn't just about data, it's about perspective. Amateurs bring fresh eyes to cosmic problems, sometimes spotting connections professionals miss. When the Eridanus Supervoid's cold spot was first debated, amateur astronomers flooded forums with alternative interpretations, from statistical artifacts to novel gravitational effects. While not all ideas held up, the dialogue pushed researchers to refine their models. Science thrives when it's a conversation, not a lecture, and voids are a topic where every observation, no matter how small, can spark big questions. The future of void hunting may hinge on this partnership. As projects like the Vera Rubin Observatory come online, they'll generate more data than any single team can process. Citizen scientists will be essential in sifting through the flood, flagging anomalies that could lead to the next great discovery. Who knows, the key to understanding dark energy's grip on voids might already be hiding in someone's unanalyzed star charts, waiting for the right moment to come to light. For anyone who's ever gazed at the night sky and felt that tug of curiosity, the message is clear. You don't need a PhD to explore the cosmos. Sometimes the most profound discoveries begin with a simple question, a telescope, and the willingness to look where others haven't. The void's mysteries aren't reserved for the elite, they're written in the darkness for all to see, if only we dare to search. The Eridanus Supervoid might seem like a passive absence in the cosmos, but its emptiness is anything but inert. This billion-light-year chasm exerts a gravitational influence so profound it sculpts the galaxies at its edges, bending their paths and altering their fates like an invisible hand shaping clay. Picture a vast, still lake where someone drops a heavy stone. The resulting ripples don't just vanish. They travel outward, nudging leaves and twigs in subtle, unexpected ways. The void works similarly. It's gravitational, dent in spacetime, subtly warping the motion of galaxies millions of light-years away. What makes this influence so fascinating is its paradox. We often think of gravity as a force tied to mass. The more matter, the stronger the pull. But voids flip this logic. Their lack of mass creates a kind of negative gravity, a repulsive effect where galaxies aren't pulled inward but pushed outward by the void's relative emptiness. It's as if the universe is a stretched rubber sheet, and the void is a spot where someone pressed down, causing the surrounding material to slide away from the depression. This phenomenon, known as the void lensing effect, means galaxies near the Eridanus Supervoid aren't just drifting, they're being herded by its absence. Take the galaxies skirting the void's edges. Observations show they move slightly faster than expected, as if fleeing the emptiness at their backs. This isn't random motion, it's a coordinated flow, a cosmic migration driven by the void's expansion. Some researchers compare it to a slow-motion avalanche where the snow is made of galaxies and the slope is the void's gravitational gradient. Over billions of years, this process can stretch galactic clusters into elongated filaments, like taffy pulled thin between two hands. But the void's impact isn't just mechanical. It also shapes galactic evolution. Galaxies caught in the void's outflow experience a unique environment starved of intergalactic gas. They age differently than their counterparts in denser regions. Without fresh material to fuel star formation, they burn through their reserves faster, becoming red and dead earlier in cosmic history. It's like comparing plants in a desert to those in a rainforest. The desert plants adapt to scarcity, while the rainforest thrives on abundance. The void, in this sense, isn't just a blank space, it's a galactic desert where survival demands different strategies. Yet there's a twist. Some galaxies within the void's grasp defy expectations. A handful of isolated galaxies, dubbed void galaxies, have been found forming stars at surprising rates. These outliers might be tapping into hidden reservoirs of gas, or perhaps their isolation protects them from the violent collisions that often disrupt star formation in crowded galactic neighborhoods. Their existence hints that voids aren't monolithic wastelands, but complex ecosystems with niches where certain galaxies can thrive. The deeper lesson here is about interconnectedness. The universe isn't a collection of isolated objects, it's a dynamic web where even emptiness plays an active role. The Eridanus Supervoid doesn't just exist, it participates, shaping the cosmos as surely as the galaxies it lacks. Its gravitational whispers ripple across cosmic time, reminding us that in the grand tapestry of the universe, nothing, not even nothingness, is truly passive. Decades of staring into the Eridanus Supervoid have only deepened its mystery, leaving scientists with more questions than answers. Take its staggering size, 1.8 billion light-years of near-perfect emptiness defies every model of cosmic structure we have. According to standard cosmology, voids should cap out at a few hundred million light-years, the natural limit of how far matter can drain away under gravity's pull. The Eridanus void isn't just breaking that rule, it's rewriting it, forcing astronomers to wonder if our theories missed something fundamental about the universe's architecture. Then there's the expansion debate. Recent observations suggest the void isn't static, it might be growing, its edges stretching faster than the surrounding cosmos. This isn't just cosmic inflation at work. It's as if the void has its own internal engine, a force beyond dark energy accelerating its emptiness. Some simulations hint that repulsive gravity, a theoretical phenomenon where ultra-low-density regions push matter away instead of pulling it in, could be at play. Imagine blowing up a balloon with a weak spot. As you inflate it, the thin patch stretches disproportionately. The void might be that weak spot in space-time, expanding under pressures we don't yet understand. But the most haunting question isn't about the void's mechanics, it's about what lies beyond it. Telescopes can only see so far, and the void's vastness blocks our view like a cosmic curtain. Is it an isolated anomaly, or does it connect to other voids in an even larger pattern? Some theorists speculate it could be part of a void complex, a network of emptiness spanning scales we can't yet map. Others wonder if it marks a boundary not just of observable matter, but of spacetime itself. Could the void be the edge of our cosmic bubble in a multiverse, a place where the rules of physics subtly shift? What keeps the Eridanus Supervoid at the forefront of cosmology isn't just its strangeness, but its refusal to fit neatly into any single theory. It's a laboratory for extremes, testing whether dark energy varies by environment, whether gravity behaves differently in emptiness, and whether the universe's structure holds deeper layers we've yet to uncover. Every answer we chase leads to two new questions, proving that the darkest corners of space might hold the brightest keys to understanding it all. The Eridanus Supervoid isn't just an astronomical oddity, it's a crossroads where cosmology, quantum physics, and even existential philosophy collide. Picture a team of astrophysicists hunched over galaxy maps alongside particle physicists running equations about the early universe, while philosophers ponder what such emptiness means for our place in the cosmos. This is the kind of collaboration the void demands, because no single field holds all the pieces to this puzzle. Astronomers measure its staggering dimensions, physicists probe its implications for dark energy, and philosophers wrestle with how such vast nothingness reshapes our understanding of existence itself. Take the quantum connection. To explain how a void this large formed, cosmologists turn to theories about quantum fluctuations during the universe's first moments, the same phenomena particle physicists study in atom smashers. Those microscopic ripples, stretched to cosmic scales during inflation, might have planted the seeds for the void's emptiness. It's as if the universe's smallest and largest scales are whispering the same secret, waiting for researchers from different disciplines to piece together the message. Teams at CERN now run simulations comparing void formation models to particle collision data, searching for patterns that could link quantum mechanics to cosmic structure. Then there's dark energy's enigma. The void's apparent expansion challenges standard cosmology, suggesting this mysterious force might behave differently in empty regions. This isn't just astronomy's problem, it's a challenge for theoretical physicists who have spent decades trying to reconcile dark energy with quantum field theory. Some now propose that collaborations with materials scientists could help, drawing parallels between how energy behaves in cosmic voids and how exotic materials like Bose-Einstein condensates exhibit strange properties at ultra-low densities. It's a long shot, but history shows breakthroughs often come from borrowing ideas across fields. Philosophy enters the conversation when we ask what the void implies about life's rarity. If such vast emptiness dominates the cosmos, does that make Earth's vibrant biosphere even more precious, or suggest life might be vanishingly rare? Ethicists and astrobiologists are teaming up to explore how discovering more voids could reshape humanity's cosmic ambitions. Would spreading life become an imperative, or would the void's indifferent expanse make interstellar dreams seem futile? These aren't just thought experiments, they influence how we fund space exploration and interpret projects like SETI. Even computer science plays a role. Mapping the void's intricate boundaries requires algorithms originally designed for medical imaging, adapted to trace cosmic web filaments instead of blood vessels. Machine learning specialists now collaborate with astronomers to train AI on void simulations, helping spot subtle patterns in observational data that human eyes might miss. One team recently repurposed earthquake detection software to identify void quakes, ripples in galaxy distributions caused by the void's gravitational influence. What makes these interdisciplinary efforts so vital is how they reveal science's interconnected nature. The void isn't just a hole in space, it's a mirror reflecting how knowledge itself is structured. Just as galaxies cluster along filaments of dark matter, human understanding advances along threads of collaboration, where insights from one field illuminate problems in another. The Eridanus Supervoid, with its blend of mystery and mathematical elegance, might be the perfect catalyst to prove that the next great leap in understanding the cosmos won't come from any single discipline, but from the spaces between them. Explaining the Eridanus Supervoid to young minds requires turning cosmic emptiness into something tangible, something they can hold in their imagination. Think of the universe as a loaf of bread baking in the oven. As the dough rises, air bubbles form and expand, creating pockets of emptiness within the soft, stretchy structure. The galaxies are like tiny seeds or raisins scattered unevenly through that dough, clustered along the edges of those bubbles while the centers remain hollow. That's essentially how voids form, except instead of yeast and heat, the forces at play are dark energy and gravity, stretching the cosmic web over billions of years. For even younger students, a sponge works wonders. Soak it in water, then watch as the liquid drains away, leaving behind gaps where the water once filled every crevice. The universe's matter behaves similarly, with galaxies clinging to the sponge's fibrous strands while voids form in the drained spaces. This analogy helps demystify why the void isn't truly empty. Just as a damp sponge still holds traces of moisture, the Eridanus Supervoid contains a faint sprinkle of galaxies and dark matter. Hands-on activities can cement these ideas. Have students blow bubbles into a bowl of water mixed with dish soap, observing how larger bubbles swallow smaller ones, a miniature version of how cosmic voids merge over time. Or use a stretchy fabric like spandex to simulate spacetime, placing marbles galaxies on its surface and watching how rolling a heavy ball, a void, across it distorts the fabric, pulling the marbles toward its edges. These experiments don't just illustrate the science, they make it visceral, transforming abstract concepts into aha moments. The key is linking the void to relatable experiences. Compare its expansion to a balloon inflating unevenly, with certain patches stretching faster than others. Ask students to imagine running through a crowded playground versus an open field. The empty space changes how they move, just as the void's gravity influences galaxies skirting its edges. Even Minecraft offers a teachable moment. Generate a vast world, then note how villages, galaxies cluster near mountains or rivers' filaments, leaving vast biomass voids where structures rarely appear. But the most powerful lessons go beyond analogies. Show them real data like the Sloan Digital Sky surveys 3D galaxy maps, where voids leap off the screen as cavernous gaps in a glittering web. Introduce citizen science projects like Zooniverse's Cosmic Web, where students can help classify voids in telescope images, contributing to actual research. When a 7th grader in Ohio discovered a previously unrecorded underdense region in 2022, it proved that curiosity knows no age limit. The goal isn't just comprehension, it's inspiration. The void's mysteries invite questions without easy answers, nurturing critical thinking. Why doesn't the void collapse? Could we ever travel through one? These puzzles spark debates that blend physics, philosophy, and creativity, showing students that science isn't a static set of facts but a living, evolving conversation. And who knows, the child who today grasps voids with bread dough might tomorrow unlock dark energy secrets, all because a teacher turned the cosmos into something they could touch. Staring into the abyss of the Eridanus Supervoid does something strange to the human psyche. It simultaneously shrinks us and expands us. On one hand, this billion-light-year emptiness dwarfs every human achievement, every empire, every dream we've ever had. The light reaching us from its edges today began its journey before multicellular life existed on Earth, a reminder that we're cosmic newcomers blinking into existence on a speck of dust. Yet there's a profound irony here. The very act of measuring this void, of wrapping our minds around its impossible scale, represents one of humanity's most extraordinary triumphs. Consider the tools we've built to study this nothingness. The James Webb Space Telescope, with its gold-plated mirrors finer than a spider's silk, can detect the heat signatures of galaxies hiding behind the void's expanse. Supercomputers crunch numbers simulating its formation down to quantum fluctuations in the universe's first trillionth of a second. Even the mathematics we use, general relativity, quantum field theory, are mental cathedrals constructed from pure reason, allowing us to decode reality's deepest patterns. That a species which spent most of its history struggling to start fires can now map the gravitational ripples of an absence spanning galaxies is nothing short of miraculous. This duality defines our relationship with the cosmos. The void shows us our physical insignificance, yes, but it also reveals our unique role as cosmic storytellers. No star or galaxy contemplates its own existence. No black hole wonders about its place in the universe. We do. When astronomers trace the void's influence on the cosmic microwave background, they're not just collecting data, they're weaving meaning from ancient light, turning photons into narrative. The void doesn't know it's being studied, but we know, and that changes everything. Perhaps the most humbling thought isn't how small we are, but how brief our moment is. The void has existed for billions of years and will persist for trillions more, long after stars burn out and galaxies fade. Our civilization, by cosmic standards, is less than a mayfly's lifespan. Yet here we are, in this sliver of time, holding up mirrors to the darkness and daring to ask questions. That's the paradox at the heart of astronomy. The more we learn about the universe's indifference, the more remarkable our curiosity becomes. So the next time you look up at the night sky, remember, you're not just seeing emptiness, you're witnessing a mirror held up by generations of thinkers, dreamers, and stargazers. The void may be vast, but our capacity to explore, to wonder, to connect across time and space through shared discovery, that's the real measure of our place in the cosmos. The mysterious void at the edge of the universe isn't just an absence, it's a revelation. Every time we peer into its darkness, we're not just studying emptiness, we're decoding the universe's hidden language. Think of it like this: if the cosmos were a book, most pages would be filled with the ink of stars and galaxies. But the voids, they're the margins where the universe scribbles its footnotes, whispering secrets about dark energy's grip, the quantum seeds of creation, and even the possibility of realms beyond our own. What makes this void so extraordinary isn't just its size or its cold spot in the cosmic microwave background. It's the way it forces us to confront how little we truly understand. For centuries, we've mapped the heavens assuming matter was the main character in the universe's story. But the Eridanus Supervoid flips that script, revealing that emptiness might be the protagonist shaping galaxies, bending light, and perhaps even steering the cosmos's fate. It's as if we've been studying the waves while ignoring the ocean's depths. And here's the thrilling part: we're only just beginning to scratch the surface. With next-generation telescopes like the Vera Rubin Observatory coming online, and missions like Euclid mapping dark energy's influence, we're on the brink of answering questions we haven't even fully articulated yet. Could the void's expansion hint at a new type of physics? Does its alignment with the CMB cold spot suggest a multiverse collision? Or is it teaching us that dark energy isn't a constant force, but a dynamic one that waxes and wanes like cosmic tides? The most humbling lesson the void offers is this: the universe doesn't owe us clarity. It's under no obligation to fit neatly into our models or confirm our assumptions. Real breakthroughs happen when we encounter something so bizarre, so inexplicable, that it shatters our frameworks and forces us to start fresh. The Eridanus Supervoid is precisely that kind of anomaly, a cosmic riddle that refuses to be solved with yesterday's equations. So what's next? The void invites us to keep pushing boundaries, to build better tools, and to stay open to possibilities that might seem outlandish today. After all, the history of astronomy is littered with ideas once dismissed as impossible: black holes, gravitational waves, the Big Bang itself, until evidence proved otherwise. Who's to say the void won't be the key to the next great paradigm shift? As you gaze at the night sky tonight, remember, the darkness between the stars isn't just empty space. It's a frontier alive with mystery and potential. The universe's greatest stories aren't just written in light, they're hidden in the voids, waiting for curious minds to piece them together. And that's the real magic of exploration. Every time we look up, we're not just observers, we're part of the conversation.